quiet when you come to class. All right. Can I get a volunteer to read a few bullet points here? What I wanted to do at the beginning of class is to contextualize what it is that we're doing now, why we're doing it, and kind of what we're going to be able to do in about a week or two. Your labs are helping you along these lines. So can I get someone to volunteer to read? Go ahead, Colin.
The EPA is concerned about a small lake. The volume of the lake is 3.5 times 10 to the 6th gallons. What is that? 3 million? At a mine just south of Little Rock, where sulfuric acid was used. The water contains many species, and we're going to focus on the conjugate acid-base pair, HSO4 negative and SO4 negative 2, due to how acid in the lake currently is.
Acidic. I should have changed that terminology. And we should also be getting pretty comfortable with our polyatomic ions. Does anyone remember the polyatomic ion on the left is called? Hydrogen sulfate, and the one on the right? Sulfate. All right, and another volunteer to read the next, or actually probably not worth reading. So if our current concentrations that we can measure in the water of those two components, that conjugate acid-base pair, are known, could you guys figure out what the pH of that solution is?
Yes.
So that's one question. For a lot of you, the answer might be no, because we haven't necessarily gone into that in this class yet, but you might have experience otherwise that would let you calculate that concentration. All right? And then the next part of the thing is, how do we make it less acidic? Talk to your neighbor for a second. How would we take this lake and make it less acidic? What are some ideas that you guys have? All right, what are some ideas? Can I hear some volunteer ideas? How do we make this lake less acidic? What are some things you might be able to do? Matt?
If you could find a microorganism that had a metabolic byproduct that was basic, perhaps it would accept some hydrogen.
Okay, we're going super into bioengineering, but yeah. Is there maybe a lower hanging fruit version of that we might be able to do? Love?
How about just add a bunch of baking soda?
So we can add a whole bunch of baking soda. Why? Why is baking soda?
It's basic.
Okay. So an even simpler version of that answer is? Add a base. And so we could do it more naturally, possibly, or we could do it more synthetically. So we could go get a whole dump truck full of calcium carbonate, limestone, right? We could dump in chunks of rock. And I'm sure our geologists could tell us a lot more about what kinds of rocks would be accessible and easily dissolvable. Calcium carbonate doesn't dissolve too easily, though, which is why it exists. But in acid rain, calcium carbonate dissolves. So anyway. So one option is proposed to dump 8.5 metric tons of calcium hydroxide into the lake. If we knew the volume, we knew the amount of base we added, could we figure out the final pH of this solution? All right, this is what I want you to be able to do, this type of thing. This is actually what happens. So a lot of old mining sites are either strongly acidic or basic, and so depending on what it is that they're trying to extract, there's a lot of leftover chemicals, and some of those chemicals are toxic because of the property of the chemical, they're metals and these kinds of things. But some of them are toxic because of the acidity or the basicity, and so you can't just open this up and let it flood into streams. So you have to treat it first in multiple ways, and one of the ways is changing the pH. So, did anyone have another idea how we can change the pH, looking at these two things, these two components? Specifically, Love?
Add more water.
Okay, so we could dilute it, and that would help. But there's actually some reasons why in our calculations it wouldn't look as straightforward. Could we add one of these two things and make it more basic? We could add the base of the conjugate base, acid-base pair, and it would make it more basic. All right, so these questions that I'm asking you guys today, you're like, of course, duh, you add base, right, to make it more basic. Once you get into the numbers, a lot of people forget that. So remember logic. You might use ice tables for a lot of things, and ice tables make you think about numbers and forget about logic. So let's not do that, please. All right. So my goals for today are that you will be able to calculate the pH or pOH of the solution if you're given Ka or Kb and the concentration of reactants, either initial concentration or equilibrium concentration. Once again, ice tables can help take the logic out of people's thought process, so let's make sure to keep that in as we go through this. I want you to be able to look at an acid or a base and say which one is more likely to give up a proton, or which one's more likely to accept a proton, more acidic or basic. And then we're going to kind of go off of this and convert between pH, pOH, concentration of H plus, concentration of OH minus. I think on some of the homework that you guys had, was it asking you to do that for today? And then the homework for Sunday has a lot more of that as well. So you'll get a chance to practice this. The activity that I handed out today also has chances to practice some of that. And then remember, I'm telling you about POGO activities that give you some chances to practice these things. Activity 45 is really good at specifically converting between pH, pOH, concentrations of those different things, and helping you think about what the concept means and what those numbers represent. And then that's activity 45. And activity 46 is if you really want to understand why something's more acidic than something else, activity 46 is really good at that. It talks about bond strength and how that relates to the ability to give up a proton, how stable is it without the proton, brings in electronegativity, and kind of wraps all those things up. If we had a 20-week course, we would be doing that activity in class. Wouldn't that be amazing? All right. And then this is something I need you guys to be able to do, is looking at conjugate acid-base pairs and then looking at salts of those. So how would we make a solution that had both a conjugate acid-base pair in it? So we're going to spend some time on that, and that's mostly going to be next week, but we'll start a little bit on that today. So we talked about Ka last class. How comfortable are you guys with the generic form of an acid and its conjugate base? All right, so we're going to be using those. So as Ka for an acid gets larger, what can we say about the strength of that acid? As Ka goes up, tell your neighbor real quick, as Ka goes up, what happens to the strength of that acid? Is it more acidic or is it less acidic? I think I heard most of the people say it's a greater strength of acid. All right, so now I want us thinking about pKa. Remember, P just stands for, we take the negative log of that, so what power it is was one of the descriptors I heard of it. So if we take the negative log of the Ka, that's going to be your pKa. So let's take a look at, I think you have a table in question number 2. You have a whole bunch of acids, and I want you to determine which of those is the strongest acid. And I want you to be able to answer that question both from the Ka, and then think about what the pKa looks like for that one as well. Go ahead and click in your answer. Letters are up here. I don't think they're on your paper. Oh, really?
There it is.
Yay, internet. All right, well, let's talk to your neighbor and figure out which one it is when it comes up.
Even though I can't answer, it's not showing.
Any of them?
The very first one worked. The second one has.
All right, I'll figure it out. All right, we have 35 responses. I cannot see them on my base station. But can I get an answer first of which one is the strongest acid? And then I'm going to come back and ask a second question. So what's the strongest acid on this table? Why is A the strongest acid in this table? How do we know that? Danielle, can I hear your description?
Word for word?
Sure.
No. I said it's the biggest boy.
What?
It's KA.
Okay, it's the biggest KA. What does that mean? What does a large KA tell us?
That it's more,
Kalia?
that it's more likely to be dissociated.
Fantastic. I love. Did everyone hear the terms that she used? Say it one more time.
If Ka is higher, that means it's more likely to be dissociated.
So if we write this generic version of an acid dissociating, then the bigger Ka, the more product favored we are, right? This is just an equilibrium constant like all others. If you get too bogged down in like the specific K and you forget about the general principles of your equilibrium constant, this becomes a lot harder. So if we say this is more product favored, then K is going to be a larger number because it's the concentration of products divided by the concentration of reactants. So your numerator is going to be bigger. That means you're going to find more of it on this side. What's another way to say there's more dissociation? What are those things it dissociates into?
You'll have a larger concentration of hydronium ions.
Larger concentration of hydronium ions, or even simpler said, a larger percent ionization. Those are two different ways you can talk about the same thing. All right? So the larger this number is, the more acidic it is. So then what happens to the pKa as your acid strength increases, and why? Talk to your neighbor about how this number relates to acid strength and how this number relates to this number. Go back to the log quiz that I had you guys do, thinking about what do logs do and what are they telling us. I'm just losing you guys today. By the way, this thing doesn't work if it's like a quarter of the people doing it. It's only when more people do it, so you look backwards and you see someone doing it. So especially the people in the back row, can you guys help me out? Thanks. All right, so what is the trend with the pKa compared to Ka, and then how does that make sense using the logic of logs? Carol?
Oh, that was not a hand raise. Well, when you have pKa, and you have that value, and you have a negative log, you're going to put that negative on the other side. It's going to be a negative pKa, and then you're going to raise that. What's the inverse of the power of 10? Like the 10 something bottom. And that's
The log. Right. So I see where you're going. I don't know that you had the most clearly thought out answer to it. So it's something to do with like you put a negative sign and then it becomes the exponent or something like that. So maybe we can...
I can draw it if you want.
If we look at specifically our strongest acid, does it have the highest or lowest pKa? Lowest. So we have the inverse relationship. I heard some people saying that. Then not only is the inverse relationship, but how does 1.99 relate to this number here? Where is that number most closely related to in this? The power. So going back to how Colin described this before, right? The P stands for what power is it. So what power is that exponent of the 10? So if you see 10 to the negative second, you would expect to see the pKa of that be about positive 2, because the negative flips the sign. So this guy down here, 2.3 times 10 to the negative 9. If you weren't looking over here, what would you expect the pKa to be? About 9, right? It's going to be a little above or below. I don't know. I don't really care if you know whether it's above or below, but it's a little above or below. You can say that it's actually a little bit closer because it's above 1 times 10 to the negative 9. It's a little bit bigger than that, which is going to be closer to negative 8. So it's going to be between 9 and 8, right? Between 9 and 8. So if you understand the power of logs, then these aren't a mystery. Then these tell you a lot about this, but it's a much simpler number. You don't need to use scientific notation. This is like a a distilled down version of that. But you need to know that the difference between these two is an order of magnitude. It's 10 times more likely to give up a proton, or less likely to give up a proton if you compare the top one to the second one. So every change in 1 in the p whatevers is going to be a 10-fold change in that property. All right, so as pKa goes down, what do we say about the acid strength? Acid strength goes up. All right. I don't know if I can close out this clicker. It doesn't seem to want to close. It'd be great to ask another question. Okay. So I'm not able to close this thing out, but go ahead and talk to your neighbor. Look at all of these different compounds here. If you can see, are they too small for you to see? Usually it's nice to send you the clicker and then you can zoom in on your screen. I don't know if I can do that. I'll try to do that while you're taking a look here. My question is, which of these molecules has the strongest attraction between the conjugate base and a proton?
Right. So why don't we just look at some of those?
All right, hopefully you can see it on your screens now.
Yeah, kick me out.
Yeah, I did a new polling session, so you have to rejoin.
Oh,
So go ahead and type in the number of the one that fits this description the best. Anthony, you appreciate this. See that? That's minutes and seconds.
Interesting.
I've never seen that before.
Why does it do that?
I think it's because it's not connected to the internet and it's like all whacked out right now. Humphrey just refuses. He's like, not doing it. Alright, let's see if I can close this out and actually get a number. Looks like I closed it. Maybe? Maybe not. Alright, so what was the discussion? What are we looking for in order to answer this question of which one has the strongest attraction between a proton and a conjugate base? Kayla, what was your discussion centered around?
I said it's the one with the smallest Ka because that means it's a weak acid and it doesn't dissociate as easily, so it's not going to give up a proton.
Love it. Absolutely love it. So Kayla's saying because it's a weak acid, a super weak acid, that means it's not going to want to give up its proton. Why? What property does that conjugate base have? Go ahead. She's passing off someone else. What property does that conjugate base have that makes that acid really bad at giving up its proton? Yeah, so Logan said it has a covalent bond. I would argue that a lot of these have covalent bonds, right? That's a covalent bond. That's a covalent bond. That's a covalent bond.
But it's also about like how stable they are on themselves. Like how can they function without each other?
Yeah. So how stable is something without its proton partner? So that comes from one of the properties is how ionic is that bond? How polar is that bond? That's what activity 46 gets into. So if you go and check that out, look at the relative electronegation. It talks about the acidity of those bonds. So in this particular case, going back to what Kayla said, the worse that molecule is at giving up its proton, that tells you about how strong of an attraction there is between that molecule and the proton, and it's an inverse relationship. The worse it is at giving up the proton is because when that proton's gone, it's going to snap it right back up. So what do we call that property of its ability to pull a proton towards itself, or the strength of pulling a proton towards itself? So that's sharing electrons in a bond with electronegativity. What do we call the ability to pull a proton to yourself? Let me ask the question another way. What's the opposite of that? What do we call the ability to push a proton to release a proton away from us? Acidity. And so the strength of something that doesn't have a proton to pull back in is basicity. So this question is saying which conjugate base is the strongest base. And so we can look at all of these and say, well, the one that's the weakest acid will have the strongest conjugate base. And how do those guys relate? Do you remember how they relate to each other? The strength of both of those? Which one of these two is a weaker acid? Alright, so sometimes it's really easy to say, well, the bigger the negative exponent is, the weaker the acid is. But it's not the bigger this number is too, right? If you just compare numerically these two, sometimes students confuse themselves and say that the top number is actually a smaller number, but it's not. You see where you might get confused on that? We had 20% of students answer 8, so I wanted to make sure that you know that 8 is bigger than 9, and we're looking for the smallest value of Ka. And so that relationship, Ka describes how likely is it to give up a proton to water in this type of reaction. And remember Kb. What does that describe? Is it just the reverse reaction of this? This is the description of how strong a base is. That's Kb, this is Ka. And so the relationship that we want to keep in mind, Ka times Kb, is a constant. And it's all about water. So technically this top one should show water. I'm being lazy and leaving water out. It should be water plus HA gives H3O plus. Yeah, Matt?
Why would it be Ka plus Kb equals K to B?
I hopefully will show you that in a second. So logarithmic values, so it's pKa plus pKb equals 14. And pH plus pOH equals 14. So let's think about where this all comes from. So if we have neutral water, this is question 4, what can we say about the relative concentrations of hydronium and hydroxide? And I'll correct that top one just to make clear. A couple more seconds. Closing out. Oh, it's just about freezing. Yeah. Internet is not great today. Alright, so if we look at these guys and we look at our responses, I feel like Al did a good job, or that you guys are very confident in this. And it's nice when I can say, I actually agree with the majority answer. Sometimes that doesn't happen, right? So that's kind of our definition of neutral. It's actually really fun when there's a misconception and a question brings it out that strong, but it's not the case today. Alright, so one of the things I want you guys keeping in mind is that last class I talked about if you write out Ka, you write out Kb, activity 43 does this as well, and you multiply them by each other, what you're left over with is Ka times Kb gives you the concentration of hydronium times concentration of hydroxide, and that gives you, that is the constant of water. If we change temperatures, this is different. So there might be some questions you'll run across that say, well, at 72 degrees Celsius, you have this Kw. What is the concentration of hydronium? What is the concentration of hydroxide? Just be aware that this is all based on a specific value that for room temperature is 1 times 10 negative 14. So then, what is it that is the concentration of hydronium at room temperature for a neutral solution? Couple more seconds. You guys are super quiet. Check with your neighbor. Walk in and talk to them. All right. Who wants to describe why this is the right answer? Avery?
When they're equal, you basically square root that 1 times 10 to the negative 14 to get two values that are equal.
Okay, so mathematically, we know that 1 times 10 to the negative 14th equals a number times itself, if you will.
Yeah, but then to just look at the exponents, since we're looking at something with 1, you would just half what that exponent is, which would be negative 7, because negative 7 times negative 7 is, or not, well, add negative 7 plus negative 7.
Great, so you're saying both ways. You can either take the square root of this value, which means you cut the exponent in half, or you can say, well, if we know they're the same concentrations, then we know that multiplying those two would give us 10 to the negative 14. All right? You guys ready for a lightning round? No. All right? No put your calculators away. I don't know that you need... Yeah, the internet today is going to make this tricky. I don't know that you need calculators at all for this. Ready? Enter your answer next. Almost there, almost there. Closing out soon, closing out. All right, we got a lot of responses. We have a couple of kind of off-the-wall responses. 80% of people said 7. Why? Using our rule of logs, how do we look at that and answer that question? Savannah, go ahead and describe. So,
the power of whatever it's asking is like the exponent on the given.
Almost.
Or well, not. It's
The negative power
yes.
of it. So if this is a 1, then it becomes super simple, right? Then we just say, well, it's whatever that exponent is in the negative version of it. So we know that pH of 7 means we have a concentration of 1 times 10 to the negative 7th molar. Pretty straightforward. All right, next one. $15 seconds for this one. Oh, we're past 15 seconds. All right, Corbin, how would you answer this one? Why?
Because kind of just use the basis of the same rule we used last time.
Okay, so we know that the exponent, right, we're saying what is the exponent on the concentration of hydroxide? Concentration of hydroxide is here. Remember, this is what we said the concentrations were of hydroxide and hydronium in neutral water. So then the last question in this lightning round. What is the sum of pH and pOH?
I'll answer it.
And closing out. So the big question is, I'd imagine you guys are decent at math. Sweet. You are decent at math. The big question is that always true?
No, only at 25 degrees Celsius.
Why only at 25 degrees Celsius, Logan?
That's what we just went over, and it's how we got the KW earlier.
Ionization constant
The
is
formula that we have.
So it's all based off of KW, right? If KW is different, then those two concentrations are going to be different, which means that their P is going to be different, the pOH, pH, which means that the addition of those two are going to be different.
You're saying that pH and pOH are always
pH and pOH are always going to equal 14 as long as we're at 25 degrees Celsius. If we're not, then they won't. I am probably not, but someone might. Okay? Can you ever have a pH greater than 14 or less than 0?
In the real world, I would say no. I don't know. Maybe.
What does that mean? Let's think about the logs. So talk to your neighbor. Thinking about logs, what does that mean to have a pH less than 0 or a pH greater than 14? What does that tell us? All right, so I'm going to cherry pick a comment I just heard. Does this mean that we have a negative concentration? What does it mean we have a negative of? Is it a negative power? It's a positive power. So that means that a pH of negative 0.025, what is that concentration of H pluses? Can anyone do that calculation? Put it in your calculator. 10 to the negative 0.25. What does that come out to? What's that, Sarah?
The positive number, 0.62 times 10 to the negative 1.
Is that what you guys are getting? Okay, so what does that mean? Can you have a 0.5 molar solution of H plus ions? Think about a strong acid. If you have a 1 molar solution of hydrochloric acid, it's almost a 1 molar solution of H plus ions. 10 to the negative 0.25. I think you might have done to the... Yeah, I think this is actually if your pH was 0.25. If your pH is negative 0.25, it's 10 to the 0.25. Which means your concentration of H plus ions is what? 1.78 molar. I can go into the lab upstairs and get you a 12 molar bottle of hydrochloric acid. So the pH of that is very, very low. So the pH of that is negative 2 point something. I don't know exactly what it is. So just keep in mind that these numbers are based off of the low end of pH of 0 is a 1 molar H plus ion. The pH of 14 is 10 to the negative 14th molar H plus ion concentration. You can have something outside of that range. For the most part, you'll see 0 to 14. But just know that it's not locked into that. If you understand what the power means, what that P means, then hopefully you can kind of get out of that mindset that it has to be 0 to 14. However, if it's at 25 degrees Celsius, the sum of pH and pOH are still going to be 14. All right. Let's go ahead and do a couple calculations. So we're on question 7. 2 minutes. Go. Raise your hand if you get stuck. We have lots of SI people here to help today, and lots of other brains. What are you missing? You're missing something new there. Alright, if you haven't gotten the answer by now, you're doing something wrong. What are we missing? Why do we not need Ka? Have you guys memorized your 6 things? This is a strong acid. What does that mean about dissociation? Alright, so go ahead and figure out what your H+ ion concentration is and then figure out the final answer. You need to recognize our strong acids and strong bases right away and not waste time doing other calculations. We have activity 43.
Here it is.
All right. If we have our strong acids memorized, we immediately see this, CHEM1403. What happens when that goes in water? What does that tell us? It's a strong acid. Over 95% of it dissociated. What does that mean? Big. Right. Ka is bigger than 1. It's really big. We don't care. If I gave you the Ka for nitric acid, you could calculate even more specifically what the pH of the solution was. In all other cases, if it's a strong acid, assume that it fully disassociates. Unless I give you a Ka, and then you can be a little more minute than that, a little more specific. So if we say everything disassociates, that means every single HNO3 goes into water, and we're going to do a full-headed arrow. What do I have on the right side of this? And both of those are aqueous. So then, do I need to do an ice table? An ice table is a tool to say, well, what part of it disassociates? What is the equilibrium amount of H+? In this case, we don't need to figure out how much of it goes forwards and backwards because all of it goes forwards. So what is our equilibrium concentration of H+? That's the assumption we're going to make anytime we see a strong acid. If you know the concentration of H+ ions, that's usually what you use a whole ice table to figure out. This is way simpler if you have a strong acid or a strong base. So we know what that X value is because the percent ionization, the term we use over there, is 100%. So then what's the pH of the solution? How do we figure that out? Negative log of 0.45. Take a guess what ballpark that's going to be in. Is it going to be 7? Is it going to be lower than 7 or higher than 7? Lower. Why? Anthony, what were you saying?
She was telling me how she did it, and I was like, it makes sense now.
Why?
But see, I didn't understand. I mean, I got the full dissociation, but you were talking about how you skip the ice table because you understand that's full dissociation, and then you can just take the negative log of it, and that's the step I was stuck on. That she told me to do.
Nice. And then in addition to that, thinking back about what that power is going to be, right? Because that's what the negative log is trying to get us to say. What's the power to 10 of that concentration? Is it going to be a very large number or a very small number? It's going to be close to 10 to the -1 power of concentration, right? 10 to the 0 versus 10 to the -1. So I'm going to guess the pH is going to be between a 0 and a 1. If you do that, you're going to save yourself a lot of trouble. The other thing I want you to do is say, always ask yourself, the first question, if I ever ask you pH, is the pH higher or lower than 7 or equal to 7? You will be amazed at how many times that will save you. In this one, how do I know whether it's higher or lower than 7 before I do any calculations? Just an acid and water, okay? So starting off, I'm going to say it's going to be less than 7, and then I can figure out how to calculate that. Don't skip that first step of making that approximation. That ballpark is actually really important. You'll see why in just a minute. All right, so then if we do this, what did you get for numeric value, Angel? Did you calculate this?
0.35.
Right number, sig figs? pH is between 0 and 1, like we guessed, and then it has 2 sig figs, 2 past the decimal. Perfect. All right, let's go ahead and do a different one. So let's do a pH of, that was not, is it frozen? Is that what I have on the handout?
Yes.
Okay, let's put a 2 there instead of a 3. Sorry about that. What just happened? Please correct the molecule. It's HNO2.
That was supposed to be really nice.
Please raise your hand if you're stuck. Obviously check with your neighbors. I think it was KD or 100, right? Yeah, I don't know why. So the only strong base is So what information do you need to answer this question? You guys have it? Yeah. Use all the information given to you, or you could look it up if you didn't see this on the paper. Alright, so go ahead and work through it. Please raise your hand if you need help.
Yeah. I don't remember.
Oh, we can't. I thought we're supposed to check it for people. You gotta go back and check your answers. If your answers are but yeah, I answered my question is that
Well, I honestly, so I get paid Friday, which is gonna be like $5 which is fine, so I'll have like $70. Okay, I'm good. But I have I want to try that. Oh yeah, I love
I feel like we're getting further on the semester. It's harder and harder to rein you guys in. All right, how do we solve this kind of a problem? And actually, to be honest, help me out, guys. Help me out. So, to be honest, I did intend to have the question originally written the way it was, because if we found the pH, could you guys find the pOH of that last problem? Okay. That was why I originally had it written up. But this is still a useful question. So if we have a solution of HNO2, do we expect that to be, let's do the approximation first. What pH are we expecting? Is it as easy to estimate as that last one? It's a bit harder, right? But can you give me a ballpark? What is it between? What two values is a pH of this going to be between if you didn't know what you were calculating? If you didn't know, if you hadn't already done the calculations. Sure, you can look at the Ka if you want. I don't think that's necessary. Is it above or below 7? This is a really important question. Is the pH above or below 7 in this problem? Why would the pH be below 7 for this problem? Same pH, not pOH. So it's an acid, it's in water, the pH is going to be less than 7. All right, done for that part. What is it going to be a higher pH then, knowing the problem that we just worked? It's going to be higher than the pH of this concentration of a strong acid. Does that make sense? This one we know it doesn't fully dissociate, so we know it's going to be between a pH of 7 and a pH of, what did we end up finding here? What was the pH of that last problem? 0.35. Somewhere in between in that range. If you can get yourself there, you're going to have a much easier time answering the question. Okay, so then how do we find what that pH is, or how do we answer this question? What are the steps you'd go through? Echo, do you want to share what your group did to kind of work through this?
Yeah, so made a rice chart,
and they were like, you know, because it's a weaker acid, you gotta build the right chart. And so I had x squared over 0.45 minus x, but there was something in the homework that was saying like if the Ka number is like has a difference of over 100 times less than the concentration of the acid, then that minus x in the denominator is negligible. So I just did 0.45 times the Ka value and took the square root of that and got for x 0.0179.
Okay, pause. Thank you. So what you're saying is that you filled out an entire ice table. This is what comes out of the ice table, is what are equilibrium concentrations of all three of these. We know that it's not a strong acid, because if it is, this would be, x would be 0.45. You guys see that from the last one? So if you have a strong acid, x is everything. Remember, this is just a tool to get us where logic should take us as well. It gives you a more specific answer. So if we say that the amount that this associates is going to be a very small portion of the total, then we can say, well, that's about the same. And your homework gave you a tool that had you multiply.
It was saying like if it was like 100 times difference or something like that over between that Ka and that acid number, then you can treat the x like this negative.
Yeah. So it's a way to kind of determine if you can use the approximation.
And eliminate the quadratic.
And eliminate the quadratic, which is our goal in all of chemistry. My goal in all of chemistry. All right. So then you can solve for x. And what did you end up finding for your x value, Echo?
I got 0.0179.
0.01?
Yeah, 79.
All right. Straightforward, right? Now we just take the negative log and we're done. Oh. So why not? What is the negative log of this number going to give us? So did anyone do that? What is the pH of the solution?
1.75.
It just happens to be 1.75. Okay, because 10 to the negative second, it's just a little bit bigger than that. Okay. First I thought you just like said that number, and I was like, wait a second. Sometimes happens if they're close numbers, all right? Great. So does that make sense with our original estimation? Between 0.35 and 7 is somewhere in that range. Good. But then how do we answer this question? That's one way. Did anyone answer it another way? Is there another way we can answer this question? So if this number is our concentration of H3O plus at equilibrium, could you find our concentration of OH minus at equilibrium? We know one of them, we don't know the other, but we know they equal. So you could find the concentration of hydroxide. And then from there, you could take the negative log of the concentration of hydroxide. It fits together. I just want you to see there's multiple ways to answer these questions, so don't get stuck in one pathway and try to memorize that pathway. So what did we get for our value of POH on that last one? 12.25. Sound reasonable? All right. So with any solution that you calculate the concentration of H3O plus, you should also think about what is the concentration of OH minus, what is the pH, what is the POH. Once you have one of those four, you can calculate all other three. And the assumption, unless you're told otherwise, is that we're at 25 degrees Celsius. Could you calculate the pH and the POH of this solution? All right, practice for you later. So let's spend the last little bit of class talking about the strength of a base. So far we've just said, well, whatever our acid is without the proton, that conjugate base is what we're looking at. But I want you to start recognizing that bases are not just something with a negative charge. That you can have bases, things that accept protons, that are not OH minus, that are not acetate that are different. What property does this particular molecule have that allows it to act as a base? If you drew the Lewis structure, you would draw a lone pair of electrons on that nitrogen, right? You notice that water has been acting as a base over and over again? Also has extra lone pairs. So it turns out nitrogen is a better base than oxygen, unless oxygen has... That's a really good base. That's what all of our strong bases have in common, is the hydroxide ion. But if we're talking about weak bases, water can be a weak base, but it's a pretty bad weak base. It works, right? Because in this equation here, that's what's accepting the proton from our weak acid. But here, whenever we see a nitrogen, if it has a lone pair of electrons, we're automatically going to call it a weak base. And then what does it look like once it accepts a proton? What property does that nitrogen always have once it accepts a proton? Is this too simple of a question?
No lone.
Fantastic. No lone pairs and a positive charge. If we ever see nitrogen with a positive charge, we're going to call that typically an ammonium. Remember your polyatomic ions? NH4 plus is ammonium. We'll call something dimethylammonium is a compound we'll talk about in a minute. So we're going to look for nitrogen with a positive charge. If it has a hydrogen, we know that that's an acid as well, because it's going to be able to give up that H plus and go back to neutral nitrogen with the lone pair. Carol, did you have a question? All right. So I want us thinking about describing, is this equation right here Ka or Kb? It's describing how capable is this thing of pulling a proton from water. That's describing Kb. So once again, we can describe Kb by the concentration of products over reactants once we've written out Kb. So the basic strength, as Kb gets bigger, what can we say about the strength of that base, or the ability to pull a proton to itself? You guys feel comfortable with which way it goes? Stronger the base, the larger the Kb value is. Because remember, it's describing this relationship here. The more it's able to pull that proton from water, the larger the top of this is going to be, and the smaller the bottom, the fewer of these we have without a proton. So we have a list of Kb's that are very blurry, but I think they're also printed blurry on your page. Is that right? So I want you to look at those, and I want you to answer question 10. Click that in. If it goes live. Don't say that the metal itself is that. Oh, it's fine. I didn't want to.
Oh, okay.
Okay. Yeah.
Oh, so right there.
That's the thing that gives us a
So it's so weak that it doesn't even have a or does not. So it's one that actually does. So NO3 unless you hear otherwise, you're always. All right, we have a lot of answers clicked in. Cycling through. You literally have one that says invalid response. I'm not sure how you guys pulled that off, but congratulations. There might be a sensor in there that like filters out bad language. I don't know. All right, so I'm going to try to take a look at the results, see if we can see. So our majority answer is 0.00067. So where does that number come from? So can I, Austin, you want to volunteer?
Oh. Well, I was just complaining about something, but KW is going to be 1 times 10 to the negative 14 equals our KB, which is for NO, we're doing NO3, nitrate.
So is this the weakest base in the table? This is a little bit kind of tricky wording in that it is so base that it's negligible. So I wouldn't even call it a base.
So we use the next one.
Okay. So fluoride.
1.5 times 10 to the negative 11 for our KB.
Right. And then what do you do with that?
Substitute in, we got to multiply by KA. But since we don't have KA, we end up dividing our KW by KB.
Great. All right, so this is a question just saying that if we know a really, really, really bad base, we're going to know what the strength of the conjugate acid is. So is HF going to be a relatively strong acid or a relatively weak acid? So I think we found that Ka equals 6.67 times 10 to the negative 4. Is that right? All right, so 10 to the negative 4. What I want you guys to do, the more times you practice with looking at a table of Ka values and Kb values, you're going to start to get a feel for what is a weak acid, what's a really, really weak acid, what's a weak base, what's a really, really weak base. And so what we take home from this is if you have HF releases a proton and goes to F minus, then this base is less of a base than the acid is an acid. Does that sound confusing?
Yeah.
Where is the point at which you would say that it's the conjugate acid-base pair is as much an acid and a base on both sides? At what point will the Ka and Kb be about the same? 10 to the negative 7. So if we have a Kb that's about 10 to the negative 7, then the Ka is going to be about 10 to the negative 7. Right, because Ka times Kb. So in this case, we're going to say, well, I know that this is the conjugate base of something that is really considered an acid. It's a weak acid. It's a little bit semantics, but I want you thinking about what the relative strength is. So NH3, if you compare NH3 and NH4+, we're going to think of that really as a base, a weak base, and its conjugate acid. So maybe it'd be worthwhile to write up something that hopefully will be helpful. Let's think of the pKa and the pKb of a conjugate acid-base pair. If we have a strong acid, Ka value, I think nitric acid is 28, but a lot of them are like 1,000,000 or something like that, right? What is the pKa of this? This is negative log of 28. What is that? What's a negative log of 28? Anybody? So then what's our pKb? pKa plus pKb equals pKw, 14.
Weak acid, strong base.
All right, so here's the thing though, is a lot of people say, well, if it's a weak acid, it has a strong conjugate base, and that is wrong. It's all about the relative value. So in this case, we know that this is a strong acid, and the conjugate of that is, I would say that this is not even a base. It's so bad of a base that it's not a base. Love?
Okay, so wouldn't the pK be negative?
Yes.
And then your
That
pK
would make more sense.
And that would be plus, that would be over 14?
That would make sense. All right, so then it would be
15.45.
15.45. That helps my argument. Thank you. I hadn't done this math in my head before. All right, so I think we just forgot the negative log of 28 when we did the negative. So if we have a little bit of a weaker acid, then pKa of that is about 4, right? So what's the pKb going to be? About 10. So what you're going to see is that as one of the sides of the conjugate is stronger, the other one moves into the weaker side. But the thing I don't want you guys to say is that this, being a weak acid, has a strong conjugate base. Doesn't make any sense at all. The two values are related by their relationship, that these two will add up to 14. But that value will never take something that's weak and have something that's not weak on the other side. So weak always relates to weak. If you have one of your strong bases or strong acids, you're so far up the charts here. We're going to do negative 1.5, right? It's so strong that that means that that ability of that conjugate to pull in a proton or pull off a proton from water doesn't exist. So do not use the term weak. This is a total misnomer. I want you using your logic, thinking about how strong is that pull between the proton and the conjugate. Still have you guys for 2 minutes. So, let's do hardest problem of the day. Does that sound good? All right. Maybe this isn't the hardest problem of the day, actually. Do you guys know how to set up and solve this problem? The big question I'm going to ask you, read this question and then I want you to answer me, what would we solve for with x? What is x going to be in this problem? Can we just take the negative log of that and get the answer? Why? So strong base is something, remember, with an OH minus and then a metal, usually lithium, sodium, potassium, calcium. All right, so we can't do that. So we have to use an ice table and KB to find X. But here's where most people get lazy or just forget. They get stuck in a habit. They say X. X is going to be the concentration of H plus ions, right? If you write out an ice table, what is X in this case? If you're using KB and you write out your KB expression, then what you're going to solve for X is the concentration of hydroxide ions. Be really, really careful. The last thing I'm going to leave you with, because it's going to be on our pre-class quiz, is this question right here. What would the pH be of a solution of dimethyl, 2 of them, ammonium, what does that tell you? does it have its lone pair? The nitrogen? No. The ammonium is no lone pair. So it has a positive charge, but then it also is a salt. N with a positive charge has 2 hydrogens and a chloride. What's the pH going to be of that when it goes into water? You want to click in your answer? I want to see your responses. Couple more seconds. So in class next week, we're going to talk about why that's going to make an acidic solution. And your pre-class quiz for Monday is going to be about this. Your homework will help you a little bit with it as well. All right, have a good week, guys.
I have a question. Could we potentially, like, what are you going to do with